Welcome to the first edition of New Masters of Science. This is the premier program of a series that introduces students and teachers to the scientists and disciplines leading the quest to understand how our universe works. Our first subject is superconductivity. You will meet Dr. Paul Chu, director of the Texas Center For Superconductivity at the University of Houston, known locally as TcSUH, and the crack team of researchers that have led the race to discover and develop high-temperature superconductors. At the same time, you'll learn that this is a race that involves many types of people besides this one group at TcSUH, and it could involve you. In this first program, we're going to learn the basics of superconductivity. These are some of the same principles you'll learn in classes such as physical science, chemistry, and physics. The secrets of superconductivity and electricity in general lie in the tiniest of regions, the molecular and subatomic scale. In the next 4 tapes on superconductivity, we will explore how these infinitesimal events have the power to impact the lives of each of us. First, we'll see the struggle to make superconductors more useful. Then we'll learn about the one topic we have omitted from this tape, magnetism, and its surprising role in levitation and superconductivity. And finally, in the last 2 tapes, we'll learn how scientists manipulate molecules shaped like soccer balls and layers of material only atoms thick in order to bring about the next electronic revolution. So join us as we help to answer the question, what is superconductivity? In early 1987, a group of scientists, including Dr. Paul Chu of the University of Houston, published a series of scientific papers announcing to the world that they had found a compound which would superconduct when cooled by liquid nitrogen. The discovery by the University of Houston and the University of Alabama made international news. All over the globe, universities, large corporations, and government laboratories began confirming these incredible findings and participating in the search for materials that will become superconductive at even higher temperatures. Talks given by this group of scientists packed lecture halls with scientists and news cameras, and for some time, Dr. Paul Chu reached near celebrity status. What is superconductivity? And why is there so much interest in finding new materials that will conduct without resistance? What would you say if you knew that even a high school student like yourself has as much chance as anyone to understand what superconductivity is and what superconductivity will mean to your future? This is the Texas Center for Superconductivity. A unique combination of state and private funds built this $22.5 million facility within 5 years of the announcement of high-temperature superconductors. It contains laboratories, a linear accelerator, auditoriums, and offices for staff and researchers. The staff is as unique as the building.
I think the important thing is we have to get people from physics, chemistry, engineering together. And so those are the disciplines we're involved. From the engineering areas, we have chemical engineering, electrical engineering, mechanical engineering. And so those are important. From cultural point of view, I think the Western culture is very good because particularly in the United States, we put a lot of emphasis on individual creativity. But it just happens here, we have quite a few people from the East, and they realize how important for people to work as a group. So those are the major ingredients.
And it's not just professional researchers and doctors of science who are involved. Students, graduates, undergraduates, and even high school students have joined in the race to understand superconductivity.
When I came here, I realized that the superconductor can enable, doing, bearings, and there was only one other group in the world at that time doing, bearing work, and I really wanted to do this. And being an undergraduate, it's difficult, but I got with the right person, Dr. Chu, who has been some great inspiration and a father to me.
The study of superconductivity allows a unique view of the modern scientific process in action.
The interesting thing is this, as this whole thing develops, and we can see the impact of high-temperature superconductivity. It has changed many, many things. For example, it has changed the sociology of the American scientific establishment. In the old days, when people did science, mostly they are restricted in the Ivy League groups, and they stay in their lab and did what they wanted to do. And now here, we are talking about not just this group of people, we're also talking about people from industry and also from federal laboratories. So for the first time, people decided to merge together and try to do something and push the frontier, the frontier back, and try to move forward as quickly as we can.
A material that passes electrical current with no energy loss is said to be a superconductor. The way we tell that there's no loss in the superconductor is to measure the voltage across the sample. If there is no voltage drop and current is passing through, then the material is superconducting. In order to understand what is happening, it's necessary to know some basic concepts of physics and chemistry.
I think we should have a basic understanding that how material forms. For example, when you put hydrogen and oxygen together, we get H2O, water. And exactly what is binding these two atoms together. So essentially, basic electromagnetic force between them. I think we have to understand why certain elements behave different from other elements. So therefore, we have to look into the periodic tables. And those are the very fundamental things, concerning oxidation, reduction, electron transfer, all those. I believe those things we can learn in high schools, and that will be very important for them to understand what's going on in superconducting materials.
In order to discuss the topics of atoms, subatomic particles, and molecular structures, it's helpful to use animation, since none of these things can be seen with the eye or even the most powerful microscope.
And 1 angstrom is a hundredth of a millionth of a centimeter. So a half an angstrom is the Bohr orbit for hydrogen. So a tiny little proton in the middle, electron on the outside, with a Bohr orbit of half an angstrom, a radius of half an angstrom. So 1 angstrom is the size of a hydrogen atom, because that's the orbit of the electron. When it bonds, it might come closer or further apart. So size is a little bit of a flexible concept.
Scientists use the observable properties of matter, the way atoms and particles interact with each other, in order to understand what is happening in the tiny atomic scale. The atom consists of 3 basic parts: the electron, the proton, and the neutron. The electron has a negative charge. The proton has a positive charge. The easiest way to remember which is to remember that both positive and proton begin with the letter P. The first rule of charge is opposite charges attract each other. Attraction means that electrons and protons will move towards each other unless they are stopped by some other force. To make things easy, we reserve the right to tack these particles down to one location. In reality, it's almost impossible to confine a particle to one location, but in this series of videos, we attach the following warning label: do not confuse animation with reality. When we replace the proton with an electron and bring in another electron, watch what happens. They repel each other. This brings us to our second rule of charge. Particles of like charge repel each other. When an electron and a proton are free to orbit each other, what we know as the hydrogen atom is created. The proton's mass is 1,836 times greater than that of the electron. Under the right conditions, the electron and proton can combine into the third major particle, the neutron. It is a heavy particle with no charge. The neutron's mass is only slightly larger than the mass of the proton. Whoops, the neutron decayed. Neutrons don't stay around very long by themselves. If we add a proton and 2 neutrons to the hydrogen nucleus, another electron can be attracted, and the atom is changed into the very stable helium atom. At its lowest energy, its least excited state, the electrons orbit in a sphere about the nucleus. Recall how we said that helium is very stable. The stability is the result of the way the electrons spin. They each spin in opposite directions, called up and down. This is the only way that two electrons may occupy the same orbit. The spin of electrons will be important to our understanding of superconductivity. We say that the helium atom's s orbital is filled, since both spins are present. But not all atoms have neatly filled orbitals. Sometimes there are available states where an electron of the right spin and energy could fit. Sometimes there are just a few electrons in higher orbital, circling around a filled core orbital. We call the electrons in the outermost orbital valence electrons. Atoms with valence electrons tend to share electrons in order to reduce their total energy. They bond.
There are perhaps 3 or 4 types of bonds in materials. If you ask why does argon or neon, which has completely closed electronic shells, if you ask why does that form a crystal, the reason why argon forms a crystal is a rather complicated interaction between the atoms. It's called a van der Waals interaction. And that's a complicated interaction having to do with the charge, or it's called an electric dipole interaction, but it's a charge-charge interaction between these things, which is attractive. It keeps them, pulls them together. It's a weak interaction, and therefore argon is a gas at room temperature. It only makes a liquid at lower temperature, and finally a crystal at very low temperature. So things which have only van der Waals interactions are usually very weakly bonded. We next go to ionic bonds. That's in sodium chloride. That's an electron transfer. Sodium says, I have an outer electron hanging out here. Chlorine says, I have a missing electron in my outer shell. Let's transfer that electron over, complete the chlorine shell, complete the sodium shell. Boom. So it's transfer, electron transfer. And that electron transfer is a very strong attractive interaction. And that's the second kind of bond. A third kind of bond, which takes place in a material like this, is in silicon. Silicon has 4 outer electrons. Like to have 8. Every silicon atom would like to have 8. They have 4. They say, gee, tell you what, I'll join up with my neighbors. In fact, I'll join up with 4 neighbors. I'll get 1 from this one from this one, well, I have to go in the middle here. 1 from this one from this one, 1 from this one, and 1 from that one. Then the one in the middle will say, gee, now I've got 8. But every other one thinks the same. And so it's called electron sharing or covalent bonding. And that covalent bonding, essentially covalent bonding, is what's responsible for the tetrahedral-like nature of this. They share the electrons, and in so sharing, lower the energy of the structure.
Bonds are the glue and springs that hold together the patterns of molecules that make up the infinite variety of matter that we see around us. In a solid, patterns of molecules can form a crystal structure or lattice. There is more space in a lattice than there is matter. This is because the mass of each of the atoms is mostly centered at the nucleus. The electrons themselves are moving so fast around the nucleus that they behave both like particles and waves. When the atom is excited, electrons can gain enough energy to change their orbital. If enough energy is absorbed, they can escape and become free electrons. The amount of charge passing through a cross-section of any material is called current. A material that does not affect the energy of the electrons traveling through it is called a superconductor. Both the electron and the proton charge cause a disturbance in the space around them. That disturbance is called an electric field. The electric field results from the positive and negative charges of the electron and proton. Electrons can collide with nuclei and each other and bounce around like billiard balls. But like waves, they can flow around objects and penetrate matter. This phenomena is called wave-particle duality and may be a little hard to believe, but experiments have proven that matter can behave like a traditional particle or an energy wave. This means that when we calculate mathematical models of tiny, fast-moving things like electrons, We may describe them as waves or particles, whichever fits the situation best. Now let's look at a large lattice of material. At one end, we'll put a bunch of electrons. At the other end, we'll put a bunch of positive ions. A positive ion is an atom with more protons than electrons. A device that does this for us every day is a battery. Immediately, an electric field is set up. The free electrons, representing a negative charge on the left, will be attracted to the positive ions on the right, which are locked into the lattice. If the lattice material is a conductor, like copper or gold, there will be many loosely attached or free electrons, almost like a gas within the material. The electrons will begin to drift out of the left side, where there are many electrons, to the right, where there are less electrons. If the material is an insulator, like glass, the lattice is tightly bonded with few free electrons, and the electrons cannot drift as easily.
The insulator, what happens is you have a conduction band totally empty here, and then you have a valence band down here, it's completely filled. So therefore, you don't have electrons to move around. In order for electrons to move around, you have to fill this conduction band partially. Once that is filled partially, then you get a metal. As a result, for insulator, when you cool it down, you plot resistivity as a function of temperature. When you cool it down, the resistivity gets bigger and bigger. In other words, the probability to excite the electron from the valence band thermally to the conduction band is decreasing as temperature decreases. And therefore, the resistivity gets higher and higher. Okay? For conductor, it's a little bit different. Conductor, you already have some conduction electrons in the conduction band, and therefore, they will carry charge through. And then when you cool them down, then the scattering between the electrons and the lattice will be reduced because the lattice will be quieter, and therefore, the electrons can move through more easily. And therefore, when you look at the resistivity as a function of temperature, for conductor, the resistivity continues to drop.
In the conductor, at the lattice scale, free electrons move through the lattice as waves in the direction of the opposite charge. If the lattice was perfectly ordered, with no defects or vibrations, the electrons would carry a current without any energy loss. However, the electron waves can be scattered by lattice vibrations. The lattice vibrations are called phonons and result in energy dissipation. Energy loss is also caused by defects such as an iron atom in a copper lattice.
Are the vibrations of atoms to be seen as atoms individually in real space wiggling back and forth, or are those vibrations to be considered as waves in the crystal with each one of them having a certain energy? And the answer is both ways, depending upon which kind of interpretation you're interested in. Are electrons traveling in crystals, little particles with charge traveling, or are they waves traveling through the crystal? Answer is both. Well, now we can look at it as waves of electrons traveling in the crystal, interacting with waves of vibration in the crystal. And those two waves interact with each other, exchange energy and exchange momentum, and that's called scattering. And that's called the electron-phonon interaction.
If the electron wave scatters off a lattice vibration or defect, the energy is exchanged to the lattice, which, like a structure made of glue and springs, vibrates even more. The more the vibration, the greater the resistance to the flow of electrons. If we keep adding electrons at one end of our conductor, like the battery in this circuit, the flow of electrons will vibrate the lattice of the wire, producing enough vibration or heat to light this match. If we purposely vibrate the lattice of this coil of nichrome wire by heating it, then the electron current flowing through the wire is interrupted enough to dim this light bulb. Carbon, the graphite lead of this pencil, is a conductor also, and we will use it to demonstrate another property of electrons traveling through lattices. We now know that a current of electrons collides with lattice defects and vibrations, giving up some of its total energy in the form of heat to the lattice. If the path through the lattice is made longer, more energy is lost in the bigger lattice, and that loss results in a weaker light. Imagine how much energy is lost in the conductors used to distribute that energy. For this reason, power plants must be close to people that need the energy. Sometimes the energy of local winds or the sun can be harnessed to generate the electricity. But often other energy sources must be used, some of which are not the best of neighbors. Wouldn't it be great if there was a conductor that would allow electrons to travel through it without taking any energy from the electrons? A superconductor?
So here you have wires without resistance, where in principle you could take all the power from Niagara Falls and bring it out to California without losing anything. Also, in principle, you have a coil that can produce a magnetic field that you could put on a train and take anywhere you want. So the ideas of perpetual motion and the ideas of getting energy and the energy wouldn't decay have just fascinated people since the discovery of superconductivity in 1911.
After the initial discovery of superconductivity in 1911 by Heike Kamerlingh-Onnes in the Netherlands, scientists began the search for materials that would superconduct at higher temperatures because of the expense and difficulty of using liquid helium.
Superconductivity was discovered at a very low temperature, and we needed liquid helium in order to produce that low temperature. And working with liquid helium is not easy. Helium is the gas that makes balloons rise that you see at parties. But to take that gas and make it into a liquid and use the equipment that's associated with it is quite difficult. Not terrible, but still not easy for the average person to work with or the average scientist to work with.
The temperature past which superconduction stops is called the transition temperature. When a material is below its transition temperature, or Tc, it is said to be in its superconducting state. When the same material is at a temperature above its Tc, it does not superconduct and is said to be in its normal state. The problem is that there is no way to stop lattices from vibrating, and materials with no defects are difficult to acquire. Scientists were forced to explain how a vibrating lattice could pass current without presenting resistance. And this is the area of superconductivity that is causing some of the most intense theoretical discussion.
In a superconductor, the electrons travel in pairs, and these pairs allow you to have electricity flowing through without any decay. Now, it's hard to see why that would make a big difference, but let me give you an analogy that is sometimes used. Let's say that you go to a dance and you agree that you and your partner are always going to move opposite to one another. So if you're standing at one position, if you bump off a wall, then your partner will pretend that there is a wall nearby and bump off in the opposite direction. Now you agree to do that, and you also agree to dance something like 20 feet apart. So if you look down from the top of this dance floor, you'll see a chaotic motion, because since you and your partner are 20 feet apart and everybody else is 20 feet apart, let's say everyone agrees to this, you see people moving all over the place, and it looks very chaotic. But in fact, in each pair, every time there's a motion one way, the mate of that pair moves the opposite way. So now picture electrons going through a wire. As they go through the wire, if this electron bounces off so that it would reduce the motion in this direction, its pair picks up that motion, that momentum, by bouncing the other way. So they move through without any loss of their velocity or their momentum. And it's this attraction between the pairs and this agreement that they'll always stay in opposite motion that causes the effect of no resistance. Now the question is, how can they do this? Because electrons are negatively charged particles, and if you bring two of them together, they push each other apart. Two negative charges repel. They do this because they exist in a crystal that has a lot of positive ions, a lot of positive background. So one electron goes through and excites this positive ion. So it makes that region a little different than it was before, a little less negative than it was before when the electron was there because of the positive background. When the second electron comes through, it sees that change and it's attractive. Now, people use other kinds of analogies. For example, if you put a ball bearing on a rubber sheet or on a waterbed, and you put a second ball bearing on the waterbed, then you know that each will travel with a depression. So they carry their depression in the waterbed with them. But if they get close enough together, they can fall into each other's depression. The idea is that the background can adjust and make it more advantageous for the two to pair together as opposed to being pushed apart. And this is the essence of a theory that was developed in 1957 by Bardeen, Cooper, and Schrieffer. The three physicists later won the Nobel Prize for this theory, and it explains almost all the properties of what we call conventional superconductors. These are the superconductors that have temperatures, transition temperatures, that are not very high. The new oxide superconductors may be explainable with this theory, but it's not clear yet. And the new carbon-60 superconductors, the fullerenes, these are these soccer balls with extra electrons in there. They may also be explainable with the BCS theory. But we're trying to find out whether all the experimental data is consistent with this theory, and so far there are a lot of open questions.
But the implications of superconductivity are far-reaching. Magnetic resonance imaging is just one example of how useful superconducting magnets can be. With so many rewards to be gained, the search continued, but with limited success. Until in 1986, at an IBM industrial research lab in Zurich, Switzerland, Georges Bednorz and Alex Mueller tried a metallic oxide made up of lanthanum, barium, copper, and oxygen. A new record transition temperature of 30 K was announced and then verified. And in 1987, Bednorz and Mueller were awarded the Nobel Prize. Other small physics labs at the University of Houston and the University of Alabama were the next to shock the world. Before the Nobels were awarded for physics, they switched yttrium for lanthanum and increased the top transition temperature by 3.5 times to 95 K. This means that liquid nitrogen, which boils at 77 K, can be used. Nitrogen is the most plentiful gas in the air, and gallon for gallon, liquid nitrogen is cheaper than milk. The story of superconductivity is just beginning. Researchers worldwide are combining their efforts to make current discoveries available for practical uses. At the same time, new clues are being shared, which may lead to even higher temperature superconductors, or superconductors with more useful properties, such as flexibility. As these efforts continue to take place, we will be there. Some of the subjects we'll cover in other episodes of this series will explore how scientists and engineers have used superconductivity in medicine, industry, and high-energy physics, and where these practical applications may lead. We'll report on advances in the research of levitation and microelectronics. Finally, we'll be in hot pursuit of the latest information on a molecule of carbon that may be the building block of the superconductive revolution, the buckyball. There is so much excitement.
There are so many questions which are not answered, and those questions, by answering those questions, also having real application which is going to impact our life for the next century. And therefore, because the curiosity and also because the relevancy that drives me and attracts me into this area.
When you have a discovery that's as extraordinary as this, it will work its way into the technology and into the lives of people eventually. It may not be in 1 year or 5 years, but it will eventually work its way in. Whether it's through bearings or levitated trains or thin films or superconducting devices or microelectronics, it will eventually work its way into the technology.
This is a profession. Only when you like it, you get into it. Once you get into it, then to a certain extent, people will still support your endeavor. So essentially, they pay for your own hobby, what you like to do, and nothing can be better than that.
In science, there's always another question to answer. There's always another field to explore. There's always something new to look at. And that's what's allured me the most. And I think that's probably the most alluring thing about science.
We hope this program and its companion labs and study guide will give you a better appreciation of the importance of the skills you are learning now. This information will help all of you take better advantage of tomorrow's technology. And some of you will build on these images and concepts and become one of the new masters of science.